Hello, everybody. Let us start building up the model that is the star. In last discussion, we talked about the assumptions that we are taking in building up this model. And please go through the last discussion if you have not already, because it's always good to remember the assumptions that goes in to make a given model. Now, the variables that we are talking about. So when I talk about a model, I essentially want to know about certain variables. And these variables are the density at a given radius and time. Equivalently, we can write it as of a given mass and time, the temperature, and compositions. Remember that if there are n plus 1 compositional elements, I have n values of this capital X's, that R goes from 0 to n. Sorry, that I goes from 0 to n. And let me just remind you what are these things. This is mass of the ith divided by the total mass. So these are the different variables that one want to find out how they evolve as a function of either radius or mass, so they are equivalent. Remember that we have assumed spherical symmetry, and dm is 4 pi r square, rho as a function of r dr. This is an identity which we'll be using often. And we have this radius and time, radius or mass and time dependence. So I call spatial derivatives. When I write the spatial derivatives, spatial also means with respect to mass sometimes, because r and m will be used in equivalent way. So I will write in terms of d, and time derivatives I will write in terms of delta. This is just for our conventions that we'll be using. Okay, so now we want to see how these quantities evolve. And how do we get to that? We use the conservation laws. So first conservation law we use is conservation of energy. Now, what is the conservation of energy? The conservation of energy is that is essentially the first law of thermodynamics. Heat absorbed is change in internal energy plus the work done. Now, first we have to look at what system we are talking about. We are talking about the star, which has a spherical symmetry. So say we talk about only that thin shell in the star. The mass inside is m, and mass inside this shell is dm. So the mass, if I write in terms of radius, at this radius the mass is m, and this radius which is r plus dr, the mass is m plus dm. So I have to define a certain things. So let us do that. So it's a internal energy per unit mass of the star, per unit mass. This I call small u. Pressure I call P. So these things can be function of mass and time both. Energy going outwards per unit time, I call this L. And if it is going outwards from M, then it is Lm. So let us draw a picture here. This is R equals to 0, and this is the region we are interested in. This is at R, this is R plus dr. Now here inside this I will have a mass m, and up to this radius I will have mass m plus dm. If I talk about the luminosity, so this is R, this is m. If this L is kind of luminosity, is the luminosity here is L, that is how much this entire thing is supplying energy outwards, and here it is L plus dl. What else do we need? We have nuclear fission going on inside. So nuclear energy released per unit mass is Q. So again, I can draw another for Q. Okay, so with these, let us try to write down the first law of thermodynamics, which I have written in word form here, now in proper form. So delta Q is delta U. This delta is remember that's the time derivative, plus P delta dV. Okay, so the pressure, the work done is because of the change in the volume, so that's why I write P delta dV. Now let us look at the terms one by one. Delta U, what is U? U is the total internal energy, and we are talking about this small shell here. So we are talking about this small shell, and we are following this shell as this shell, if it is goes out or inside, we don't care. We are always following this shell which has the mass dm, right? And you will also agree that this dm is nothing but rho times dv, right? dv is the volume of that shell and rho is the density. So if the shell expands, the volume may increase, but the density will then decrease because dm has to remain same. That is how we are parameterizing. We are following that mass, we are not following that shell. Now what is U? U is the internal energy per unit mass is small u, and there is dm amount of mass in that shell. So delta U I can write this way. And then you will agree that the mass Again, I am following that mass that doesn't change with time. So this is nothing but delta U times dm. Now, delta of dv I can write as delta of dv from here is rho by dm, or dm by rho, sorry, dm by rho. And this delta is a time derivative. Again, dm will not, mass will not change. So this is delta of 1 by rho only. What about delta q? Delta q will come from two places. One is the amount of heat generated because of fusion there, plus amount of heat transferred. So the heat generated is because of that nuclear energy release, which is Q, and it's per unit mass per unit time. So if I consider in delta T time, so this is Q delta T. And what about the heat transfer? The heat transfer is because there is L luminosity here and there is L plus dl luminosity at the end of the shell. The luminosity is energy going outwards per unit time. So I can write the heat transfer as L minus, or L as a function of m minus L as a function of m plus dm. So this will be, and in time delta t, so this is per unit time, so in time delta t, it is times delta t. So this is minus del L del m dm delta t. This is my delta q. So now I have all the ingredients to write in my first law of thermodynamics. Delta q is q delta t minus del L del m dm delta t equals delta u is delta small u into dm plus this is p delta of 1 by rho times dm. If I ask the question per unit time, then everything I will, so you can first see that dm is there in all of these quantities, and again I forgot a factor of dm here because q is again per unit mass, so I should have a factor of dm here also. So that is there in all the quantities, so that goes out. And if I divide everything by delta t, I get the time derivative. So I become u, it becomes u dot plus dot is the time derivative Newtonian notation, as you know. 1 by rho, time derivative of that equals q minus del L del m. Okay, so that is our first equation for stellar astrophysics. It's coming from the conservation of energy. If the star is in thermal equilibrium, then your left hand side, which has the time derivative, equilibrium means doesn't change with time. So it's thermal equilibrium. This is equals to 0. This implies that Q minus del L del M. Remember, this L is at the radius M. This is equals to 0. So I can calculate now L. I can do the integral over L. At the center, obviously, the luminosity is 0. At the luminosity, at the edge of the star, the luminosity is that of the star. So that I call capital L only. It's a number, not a function. This equals integral of Q dm. And the integral is 0 to m. Okay. So the left hand side is obviously the luminosity of the star. So let's put a star over here. So this is the luminosity of the star. This is the quantity that we are plotting in the y-axis of Hertzsprung-Russell diagram. This equals to 0 to m q dm. This is why it is thermal equilibrium. Now, this quantity is defined as the nuclear luminosity. This is the energy produced, total energy produced by the sun, total nuclear energy produced by the star, not sun, sorry. So in thermal equilibrium, so let me write it down, because total nuclear energy produced by the star. That is here. This is the luminosity of the star. So in thermal equilibrium, they are same. Okay, only in thermal equilibrium, they are same. All right. So this is what we get from one of the conservation laws, which is the energy conservation law. So conservation of energy gave me this equation, which is one of the important equations that we will see in the theory of stellar structure. And we also understood that the nuclear luminosity will be the luminosity of the star if the star is in thermal equilibrium. Let us look at conservation of momentum, or if you wish, Newton's laws. Now, unlike energy, momentum is having a direction, it's a vector. So one cannot analyze the conservation of momentum for that entire shell, because if remember that we have this shell in which we are dealing with, we are doing all our physics, but this shell expands in different directions and different parts of the shell. So I cannot deal with the entire shell while I discuss conservation of momentum. So I have to deal with only one part of the shell. But if I deal with only one part of the shell, you see, then my mass parameterization doesn't work, because the mass is the mass in that shell. So I do it a little differently to start with. Later we can change to our mass parameterization. So what we look at now is a part of that shell. So this is only a part of that shell, and we take a very small region, and very small region I can consider it as a cylinder. I mean, if you wish, the radius of the shell that we are looking at, here it is r, here it is r plus dr. If r is very very large, so then we can consider this to be a cylinder. The mass inside this, what is called a pillbox, is delta m. The pressure at this radius is r. The pressure at this radius is p, is r plus dr. And this pillbox has an area of delta s. Okay, this is a cylindrical region. And you will agree that delta m is rho times delta s times delta m, delta r. Now what will be the equation of motion? I can just use Newton's second law. So equation of motion of the mass element. This is the mass element. The mass element is at a radius r. So the equation of motion will be r double dot times delta m, which is the rate of change of momentum, equals, there are two forces acting here. One is gravitational, and the other force is because of pressure, or pressure difference to be exact. The gravitational force is easy to write down. It's minus g, that mass delta m, and it's because of all the masses inside that radius. This is coming from Gauss's law, and divided by r square. What about the pressure force? Why there is a pressure force? There is a pressure force because I have this area on which the pressure acting here, and I have the same area on which a different pressure acting. So the difference between, so there is a force because of the pressure. Pressure is force per unit area. So force per unit area in the inner radius is PR. So the total force is PR times delta S. And outside it is PR plus dr times delta S. So I can write this as G delta M mr by r square plus, and this is nothing but minus del P del R times delta S into delta R. But you see, delta S times delta R is delta M by rho. So this I can write as G mr by r square minus del P del R. This is delta S into delta R is delta M by rho. So I put the 1 by rho here, and delta M I can take common outside, which cancels with the delta M in the left hand side. So I am left with this equation. which is the other equation of stellar structure. I can change this equation a little bit. Remember that 4 pi r square dr rho times this is dm. So for rho dr in the denominator, I can trade for rho dr dm by 4 pi r square. So the other way of writing this equation will be r double dot equals minus gm by r square minus 4 pi r square times del p del m instead of r. These are the two forms of a second stellar structure equation. Now there are two immediate things that comes out of here, and that is what we will discuss now. And both of them are the case when the star is in hydrostatic equilibrium. So let us discuss what we mean by hydrostatic equilibrium. It essentially means r double dot equals 0. What is r? R is the radius of that mass element, or radius at which you are talking about that mass element, or because once we have written these equations, considering all the vector forces and all, here I am writing it in terms of mass only. So it's the radius at which that mass shell is there. So change in the radius, or the second derivative of r, essentially tells me if that shell is accelerating outwards or inwards. If it is not, then we say it is in hydrostatic equilibrium. Now in such a case, when it is in hydrostatic equilibrium, we get gm by r square. Remember that this is a function of r, equals 4 pi r square del p del m. I can as well write dp dm here because it's not a function of anything else now. It's not a function of time anymore. I will have minus sign here. Or I see I can write del p del m, or let's write dp dm. This minus 4 pi r to the 4. I have g and m here. So m is the mass within the radius. It can never be less than 0. So m is greater than 0. R is also greater than 0, which means my dp by dm, everything in the right hand side in this small thing is greater than 0. So the dp by dm is less than 0. What does it mean? You see, mass increases with radius. Which means the pressure must decrease with radius because dp by dm is less than 0. Now you can see this in a more straightforward manner if you use this expression where you will get dp dr less than 0. But I leave it for you to work it out from that expression. So sometimes we'll write in this way: if r increases, this arrow, upper arrow means increases, mass increases and pressure decreases. Okay, this is a short form of writing those things. So let us calculate the pressure. So now safely assume, this we discussed last time also, that pressure at the mass equals to capital M is 0. That is a very safe assumption. At the surface of the star, there is no pressure. Otherwise, either the star will not stay how it will contract, which is not happening because we said r double dot is 0, or it will throw away some material, which is also not happening. Even if it's happening, it's so small, then we can consider the pressure to be 0 there. We say the core pressure, we call it PC, which is P at mass equals 0. Okay. We are writing this because now we will like to integrate this expression. Now let's try to do that. Obviously, let me write down and then we'll see where we are getting stuck and what argument we can put in against that. So this goes from the pressure at 0, which is PC, to the pressure at the surface, which is 0, dP equals minus pressure at the center is, mass at the center is 0, mass at the surface is the mass of the star, and then gm dm by 4 pi r to the 4. So you can see PC is, so the left hand side is 0 minus PC essentially. So I get PC is 0 to m gm dm by 4 pi r to the 4. Now what I should do here is to write the expression for m and dm, and the expression for m will have rho. So let's try to do that. Let's not try to do that, actually it is not required. We can argue what is the minimum value of PC that we expect. So as you can see, to do the integration here, I really need to know what is the density dependence, how the density varies with radius or mass. But say I don't know that, I can argue that this should be greater than, if I integrate from 0 to m gm dm by 4 pi, if I put anything which is greater than the smaller over here, that will only give me a lower limit of PC, right? Because it's in the denominator. If I put anything which is larger than smaller, that will only reduce PC. So why not we put the largest radius possible, which is the radius of the star here? Then I can at least say that PC must be greater than this. But if I have done that already, I can take this 4 pi r star to the power 4 outside and do the integration, which will give me gm square by 2, where m is the mass of the star. So we get the lower limit is, so PC should be greater than, it's the lower limit, I'm writing it like greater than gm square by 8 pi r star to the power 4. R star is the radius of the star. M, there is only one M, so I'm not writing it explicitly like M star. Now let's calculate for Sun. And now we see that I have to tell you the radius, the mass of the Sun. Radius I have already told you once. This 2 into 10 to the 30 kg. Radius of Sun is 7 into 10 to the 8 meter. This gives me a PC of the order of 4.4 into 10 to the 13 Newton per meter square. This is an enormous pressure, and this pressure is what ensures that the fusions will happen at the center of the star. Okay, so this pressure being so large is kind of an evidence that there is fusion happening at the center of the star. Now, for the hydrostatic equilibrium, we will talk about the relation of total internal energy and the gravitational potential energy. In hydrostatic equilibrium. This is the next topic we want to discuss. This has a name, it's called virial theorem. Remember, the hydrostatic equilibrium is the case where the radius, the acceleration is zero essentially. R double dot was zero. So let us start by writing this. This is the case of hydrostatic equilibrium. Now we are talking about total internal energy and total gravitational potential energy. So this expression as can be written as minus gm dm by 4 pi r to the power 4. But because I want to talk about the total energy inside that radius, what I do is I multiply this by the volume, which is 4/3 pi r cube, obviously in both sides. So this is my volume over which I am doing this. So let's the left hand side, let's write that as VdP. In the right hand side, I get 1 by 3 minus Gm dm by R. I want to do an integral. So if I do this integral 0 to P VdP, this I can also write as just do an integral by parts. So let's say 0 to R. So R equals to 0 to R equals to R. These are just symbolic. These are not the numbers that we will put into the integral. Okay. This minus 0 to V P dV. So essentially what I have done is the integral over P I have changed to integral over V, which obviously I have more control on. Because dV I can write as rho 4/3 pi R cube if I wish. Now, what is this middle term? The middle term is pressure at, this is the stellar radius, right? Pressure at stellar radius star times the volume, which is the total volume of the star, minus pressure at the core, which is 0, times the volume at the center, which is 0, minus 0 to V P dV I can write in terms of dm. This we have done many times. So this is just dm by rho. And you see pressure at the radius of the star is 0 and this is also 0. So this entire thing boils down to only this much. So we did the integration in the left hand side, so should we do in the right hand side? So let me write down what we get from here. So I have got 0 to V P by rho here dm equals 1/3 integral, and that integral is over m. At the radius r star, the mass is the mass of the star. We should have a minus here. Now this you will agree, for a gravitationally bound object is the gravitational potential energy. So this, we define this with capital omega, which is 0 to m minus gm dm by r. So this integral, the right hand side is 1/3 omega. So I can leave it here. So omega is minus 3 times 0 to v. So if I do not know the dependence of the pressure and the density, this is my virial theorem. This is where I can leave it. If I do not know the dependence of pressure and density. If I know the dependence of pressure and density, so that is, say, in case of ideal gas, we know that P is rho by mg times kT. And kinetic energy, so we are talking about, say, hydrogen gas. Is 3 by 2. Sorry, 3 by 2. 3 by 2 kT is the total energy, and then per unit mass is per unit mass of the gas. So that is this. So this you see, kBT by mg comes in both the expression of P and this. So we can write P by rho from these two. I can write P by rho, which is kBT by mg, as 2U by 3. So that I can use in my equation here. So I will get omega equals minus 3. P by rho is this, so that has 2 by 3. So I write 2 by 3 here outside. 0 to m u. Remember that u is the internal energy per unit mass. So it's a function of m times dm. So the right hand side, this expression gives me the total internal energy of the star. So this is minus 2 times u. So where u is defined as 0 to m u dm. So this is another form of virial theorem, where the 2 times the total internal energy plus the gravitational potential energy stays as 0. This is other important thing that we will be using later. So this, remember, is hydrostatic equilibrium. Ideal gas. We'll stop here today. Today we have discussed some equilibrium properties of the star, but more importantly, we talked about two equations. One gives you the second time rate of change of the radius, and other gives you the time rate of change of the internal energy per unit mass. Thank you.